Our final speaker before the early coffee break is Anna Schauer, who's talking on our friends, the escape fractions.
Yes,
which
thanks
there's
a lot.
divided opinion on, I gather.
Yeah, but
Right.
I'll be talking about a different kind of escape fraction. So, hi everybody, my name is Anna Schauer. I'm a second-year PhD student, actually here at the University of Heidelberg in Ralph Klessen's group. And first of all, I would like to say thank you. I'm very happy that I have the opportunity to talk today about my research project. So what I do is I study Lyman-Werner escape fractions. Jared talked a bit about Lyman-Werner radiation already, but let me give you a short recap. So Lyman-Werner feedback consists of Lyman-Werner photons in the energy of 11.2 to 13.6 eV. And this Lyman-Werner radiation is very important because it's able to photodissociate molecular hydrogen. Molecular hydrogen, on the other hand, can be self-shielding and also be shielded by neutral hydrogen. So therefore, there's an interplay of how much Lyman-Werner radiation, how much molecular hydrogen you have in order to see if you have some molecular hydrogen at all. And this is now able to regulate star formation, because when you don't have molecular hydrogen, you lose your coolant and you're not able to form stars. And when you're not able to form stars, you might set the environment for direct collapse black holes. So my job now is to calculate how many Lyman-Werner photons can actually escape from a first galaxy. So let me quickly show you my setup. I run simulations and then I post-process them. So the setup can be cartoonish pictured like this. I have some halo, some first galaxy, and at the center I have a radiation sort, which will be a SED. And then I use the code SysMP. I run it in 1D and spherical symmetry, which is probably the biggest caveat of this work. The code has included a network of primordial chemistry, and the radiation is transported in 120 energy bins. And the nice thing is that the radiation is time dependent. And what I do afterwards, so when this radiation source begins to shine, it partly ionizes the halo in different ways. And then after the simulation has finished, I do my post-process. I analyze how many Lyman-Werner photons can escape from my first galaxy. And I do this by taking the self-shielding functions from Volkert, Green, and Hyman, because Lyman-Werner radiation can be shielded by molecular hydrogen. I explore quite a parameter space. I take two different halos from the simulations, cosmological simulations by Muhammad Latif. They have the masses of 6 times 10 to the 7 and 4 times 10 to the 8 solar masses. I take them at a redshift of 10, and I assume that they are metal-free, so maybe I'm stretching this a little bit. For the radiation source, I already told you I use SEDs, which consist of a whole stellar population. I have 5 different types, going from a very extreme salpeter slope IMF with an extreme mass range from 50 to 500 solar masses down to a more normal Krupa IMF between 0.1 and 100 solar masses. In order to normalize my SEDs, I use star formation efficiencies. Actually, I calculate my fiducial cases via a nice paper last year from O'Shea. And for my less massive halo, this effectively is a star formation efficiency of 0.5% for the lower mass halo and 2.1% for the more massive halo. When I now look at my results, I would like to put them into 3 groups, depending on how the ionization front is behaving. So I'll start with the most simple case, where I have an ionization front which is outbreaking through the halo. And I'd like to guide you through my analysis. So here on the underlying plot, you can see the radius of the ionization front in black and my Lyman-Werner escape fractions in red as a function of time. And when this red line has reached the value of 10 here, this means that the Lyman-Werner escape fraction is at 100%. Overlying, I show you the mass fractions of all the primordial elements which I have, and the number density here on the right axis corresponding to the black line. So at the start, t equals 0, I have a neutral halo, 25% helium, 75% hydrogen. Now, already at the first time step, an ionization front starts pushing through the halo. it proceeds very fast. You can see here the ionized hydrogen and helium. And already at less than 0.1 megayears, the ionization front has gone beyond the virial radius. And then it stalls here at large radii, which are actually the outer radius of my simulation. And not much happens. At the same time, you can see that the Lyman-Werner escape fraction just jumped to 100% and stays at 100%. To summarize this behavior, when the ionization front is over running the halo, all the molecular hydrogen is of course photo-dissociated in the ionized region, and when I average this escape fraction over the time, I always get a Lyman-Werner escape fraction larger than 90%. As the next case, I would like to discuss what I call returning ionization front. So here I have another example. I also have the more massive halo. I have a less extreme IMF. And again, here I start with the initial conditions with the neutral halo, and quickly the ionization front is running outside of the halo. But then, since my spectrum weakens, since the first stars start to die and don't contribute to the spectrum anymore, a recombination starts to happen. You can see a little bit of neutral hydrogen appearing here. It gets more, and then it drops here. And when the ionization front is moving backwards and stalling at the shock front, you can see here that in blue, molecular hydrogen starts to build up. Because here you have perfect conditions for building molecular hydrogen. You have a density which is high, and you have a lot of free electrons, and therefore you can produce lots of molecular hydrogen via the H- channel. This continues to stay the case, and more molecular hydrogen builds up. So from this point where the ionization front was returning, the halo was reneutralizing from outside, the Lyman-Werner escape fraction dropped to 0 and stayed like that. And we can now approximate the Lyman-Werner escape fraction by this simple formula, where we can take the time where the reneutralization outside in of the halo happens, divided by the total time for which the simulation is running, and this then gives approximately the Lyman-Werner escape fraction. The third case is where I have an ionization front which is slowly moving throughout my halo. It's the most difficult case, mostly in terms of numerics, and I'm going to show you just one of my many different cases. So here I have the different halo. Again, I show you the same properties, but the scale now is different. So I can't show you the virial radius because it's somewhere here. And also for the mass fractions, my scale's going down to 10 to the minus 6. So don't be surprised that at the initial setup we have a lot of molecular hydrogen here. Again, the ionization front is starting to proceed through the halo. But this time, at the position of my now D-type ionization front, I have this massive production of molecular hydrogen. And this very thin shell, which you can see here, is actually able to block the Lyman-Werner radiation from going outside of the halo. And therefore, the halo is completely shielded against the Lyman-Werner radiation. As time continues, the ionization front is continuing to slowly move. And then something happens, then my incident spectrum changes, since it's composed of many stars and some start to die, so my spectrum gets softer. And now here you can see that I already lost my tail of molecular hydrogen, and now here this peak is starting to get smaller. So here's still a little bit of molecular hydrogen, here's a tiny bit of molecular hydrogen. But what happens here again is that the total spectrum becomes so weak that the ionization front actually starts to be returning, and then you can see it moves here back inwards, and here again molecular hydrogen is massively produced, and at the end of the simulation we again have here a bulk of molecular hydrogen. So for the case of my slowly moving ionization front, my Lyman-Werner escape fraction cannot be approximated by a value of 90% or by just dividing two numbers by each other, but it has to be a case-to-case consideration, and it's dependent on this thin shell of molecular hydrogen which builds up at the ionization front. I did this study for my whole parameter space, and I have some preliminary results for this. And I did characterize them again as the outbreaking ionization fronts in green, the returning ionization fronts in blue, and the slowly moving ionization fronts in red. And especially the values which you can see in red are preliminary and to be considered as lower limits. What you can see is that for the star formation efficiency of 1% and above, so for all the more massive halo and the lower massive halo and the most extreme star formation efficiency, the escape fractions are mostly outbreaking or returning, with two exceptions. For the most extreme salpeter IMF going from 50 to 500 solar masses, the escape fraction is also rather big. Those are both not surprising results. But what's maybe surprising at first glance is that for the flat IMF, which goes from 9 to 500 solar masses, the escape fractions can be a bit lower. So this might be worrying at first glance for the people who do direct collapse black holes. But when you then consider back how this SED is actually built, it's not so worrying anymore, because we have a lot of stars with high masses which die soon, and then the ionization front is the case of the returning ionization front, and we only have this very short time where actually the ionizing radiation is driven out and the Lyman-Werner escape fraction goes to 1. But this value can also depend a bit on the normalization. So when you let the simulation run not for 20 mega years, like in my case, but for shorter, then it's not that little. I did a similar study last year, that time not looking at the first galaxies, but instead of individual POP3 stars in mini-halos at higher redshift, at a redshift of 20. And here I show you my results for the Lyman-Werner escape fraction as a function of the stellar mass. So I covered a mass range from 9 to 120 solar masses, and I considered 3 different mini-halos of 6 times 10 to the 5 to 1 times 10 to the 7 solar masses. The not surprising result was that with higher stellar masses, the escape fraction goes up, and with higher halo mass, the escape fraction goes down. The bit surprising case here was that for the most massive mini halo, so for the 1 times 10 to the 7 solar mass halo, the escape fraction was 0 for a 120 solar mass star. We would have guessed it would be a bit more. And in this case, unlike now, when considering neutral hydrogen shielding in combination with molecular hydrogen shielding, we can see that at the low mass end of my stellar sources, this neutral hydrogen plays a role. So you might overestimate the Lyman-Werner escape fractions by a factor of 3 at this low mass end if you forget to include shielding by neutral hydrogen. I'm already at the end. I'd like to conclude. So for my Lyman-Werner escape fractions from the first galaxies, I can characterize my results by the movement of the ionization front, and I'd like to put them in 3 groups. So one is where I have an outbreaking ionization front, and there the Lyman-Werner escape fraction is 100% after the outbreak, and in general larger than 90%. Then I have the case where I re-neutralize the halo outside in, because the spectrum weakens since stars are dying. And there I can approximate the Lyman-Werner escape fraction by the time when this re-neutralization is happening, divided by the total runtime of my simulations. And then I have the case where I have slowly moving ionization fronts, which are very much dependent on the buildup of a thin shell of molecular hydrogen, which is able to shield the rest of the halo from the Lyman-Werner radiation, and therefore this very much depends on the microphysics. Considering my single POP3 stars in mini halos, the escape fraction can be very small. It can be at 0% if I have a massive halo. And for my individual POP3 stars, the shielding by neutral hydrogen plays a crucial role when you consider lower mass stars. And with this, I would like to thank you and hope you have some questions for me. Thank you.
I see an eager questioner up front.
So I have one question and comment. So the first I give comment. So I think the escape fraction very the 0% is a bit sound misleading because the Lyman-Werner absorption in only lines. So even if the escape fraction is 0%, photons in between the lines can escape. So if there is some velocity shift between the halos, the nearby halos can be photodissociated.
I agree. And if I had more time, I would have explained that I'm actually considering the Lyman-Werner escape fractions in two limits. So what I talked today is the so-called near field, where I use the self-shielding functions and where I'm sitting at the line centers. But I also did in my previous paper consider the so-called far field, where I'm calculating the combined equivalent width of all the single Lyman-Werner lines and compare it to the total Lyman-Werner range. And there, the escape fractions are much bigger. Yeah, in fact, you can see this plot here. So the escape fraction are much bigger. But for one case, for the 10 to the 7 solar mass halo, the escape fraction here is at 70% and not at 100%.
Okay, and so my question is also related to your previous slide. So can you go back to the? Yes, and so you do not include the velocity shift effect inside the halo?
No, so my radiation source is at the center and not moving.
Okay.
Okay, Raffaella? Okay, I'll be next. Go ahead.
Okay, so you said that the escape fraction also depends on the size, the mass of the halo. So
yes.
Have you also looked at the internal structure of the halo, like if it's like triaxial or more prolate or oblate, and depending on how your stars are interacting with the directionality, like does that change a lot, or do you just assume spherical symmetry?
I do assume spherical symmetry, unfortunately.
Okay, Raffaella?
So I probably may have missed something, but so at a certain point in your simulation, you said, of course, that your spectrum will going to soften because you have your stars which are disappearing, but some of them will explode as supernovae, and when they explode as supernovae, they will change the density distribution around them, and if you think they are also producing dust, they may, provide additional opacity to even Lyman-Werner radiation. I don't know if you have any thoughts on that.
So that's a very good comment. What we assume is that the stars, when they die, they will instantly form a black hole. So we don't consider the supernova explosions. I think it would break the parameter space completely.
And Dan had a comment or a question.
I just wanted to address really quickly the last two comments. So Bhaskar, your comment is really interesting, and we considered doing this in ENSO, in 3D, but we found that even with AMR, we couldn't resolve that molecular hydrogen shell well enough. We really, computationally, could only do it in 1D, unfortunately, but we're still going to go after that if we can. And Rafa's comment's really good too. In principle, we can model that in Zeus because we have dust absorption to UV, and we could, in principle, blow that star up and then assume wherever metals go, there's dust, and then we have dust opacities already built into the RT, so that'd be a very nice follow-up calculation.
Okay, any other comments or questions for Anna? If not, we'll go to, well, let's thank Anna again.